In this video, we are going to learn how to detect lines. Specifically, we will use Hough transforms to detect lines. So we will talk about what is the Hough transform and how can we use Hough transform to extract line segments. We will use the example of lane detection. Let's switch to MATLAB to look at this. Right-click on ijvcvideo.avi and open it outside MATLAB. Here, we see someone walking through a course. Knowing where the white lines are, the robot can navigate while staying within these white lines. In this video, we will see how to detect a line in an image mathematically. Let's go back to the presentation. We can use the standard Hough transform to measure the lengths of lines. Suppose that there is a line in an image that needs to be detected. In general, any line can be represented using the expression y equals mx plus c, which means every line can be mapped into a coordinate pair m, c. However, for vertical lines, this presents a problem with the slope value being unbounded. So the Hough transform uses a different parametric representation where every line can be associated with a parametric pair of theta, rho. Here, rho corresponds to the distance from the origin to the closest point on the straight line, and theta is the angle between the x-axis and the line connecting the origin with that closest point. Conceptually, Hough transform is the mapping of image coordinates in x, y into these parametric coordinates theta, rho. Next, let's see how to use this Hough transform to detect a line. For example, suppose that our image consists of a line as shown here. A line is made up of multiple points. Similarly, multiple lines could pass through the same point. When we visualize this in the Hough transform plane, where we have the Hough parameter theta on the x-axis and rho on the y-axis, every point in the image plane is transformed into a sinusoid. This makes sense because many lines may pass through a given point in the image plane, and this translates into a sinusoid in the Hough plane. If a pair of two or more of these points coincide to form a line in the image plane, they will intersect in the Hough transform plane. This intersection corresponding to a theta, rho pair corresponds to the detected line. The number of sinusoids intersecting determines the strength of a particular line. This is how Hough transform works. Next, using the Hough transform technique, let's see how to extract line segments from an image in MATLAB. We see the example image here. First, we create the Hough transform matrix using the Hough function. Then we locate the peaks in the transform matrix using the Hough peaks function. The peaks correspond to the intersection point in the parameter plane, so each of these peaks is a detected line. Hough lines function is then used to map the peak back into the image plane and extract the line segments. Now, let's take a look at the Hough transform for simple images to understand the workflow involved. Let's switch to MATLAB. Let's open the starter script Hough_start. Let's run this code. Here we see two images. We will try to identify the line passing through these two dots and the line in the second image. Note that these are binary or black and white images. All the functions here related to the Hough transform work on black and white images. Let's go back to the code. Let's first work on the image with two dots, so let's select the image with a line and then comment it using the shortcut Ctrl R. We will now compute the Hough transform matrix using the Hough function. This function takes in binary or black and white images as input, so we can directly pass the image here. This returns three outputs: the transform matrix itself, H, and T and R these are the arrays corresponding to theta and rho parameters over which the function generates the transform matrix. To visualize the Hough transform matrix result, we will use the utility function provided, HoughMatWiz. Let's open this. The best way to visualize the Hough transform matrix is as an image. We convert it to a grayscale image and adjust its contrast. We can also specify a color map to highlight the values with the corresponding colors. Let's go back to our script. Let's visualize the result using the HoughMatWiz function that we just discussed. Let's run the code. We see the two sinusoids that correspond to the 2 points in the image. The Hough transforms of all the points in an image are added up in the Hough transform matrix. So, points where the transform sinusoids intersect, example, sinusoids corresponding to the points on the straight line, become larger in value. Therefore, peaks in the transform matrix H represent potential lines in the input image. We can find these peaks using the HoughPeaks function. Let's go back to the script. Let's find the peaks. Notice that we can provide the number of peaks to be returned as an input argument. If we don't provide this, the function returns the largest peak. Let's run this code. Go back to the command line. Here we see H peaks to be a 1/2 array. This is the pixel location at which the peak occurs. Let's go back to the code. We can figure out wherein the H matrix this occurs by indexing into theta and rho arrays and the peak pixel location. We can then plot this on the H matrix. Let's run this code. Now we can see the peak location on this plot. This peak refers to the line that goes through the two image dots. Now, let's apply the same logic to the image with a line. Let's go back to the script. Let's copy the code here and then paste it here. And we will also uncomment the code that corresponds to the image with the line. Change the input to the Hough function from A to B, which is the image with the line. Let's also change the plot order here. And then let's rerun this code. Now we can see the Hough matrix corresponding to the image with the line as well. We see the single peak corresponding to a single line. We also see many sinusoids. Each of these corresponds to the point on the line. Now the final step is to map this peak back into the image plane and extract the line segments. We can do this using the HoughLines function. Let's go back to the script. The HoughLines function takes the original image as the input for the image plane reference, followed by the array of theta and rho values and the peaks which need to be mapped back into the image plane. Let's run this code. Let's go back to the command line. The output of HoughLines is an array of structures with the number of structures equal to the number of lines detected. In this case, there is only one line detected. Let's double-click on this variable. We can see the 2 points connecting the line and the corresponding theta and rho values. Now, using this information, let's redraw the detected line on the original image to see if the detection worked. To do this, let's go back to the script. Using the HoughLines structure, let's create an array of points. Then, on top of the original image, let's plot the points with a different line style, color, and width. Let's run this code. In this figure, we see the original line, and the dashed line represents the detected line. So in this way, we can use Hough Transform to detect lines in a black and white image. Let's go back to the presentation. To extract line segments in an image using the Hough Transform approach, we talked about 3 steps. First, we create the Hough Transform matrix using the Hough function. Recall that this took binary or black and white images as input. Then we locate the peaks in the transform matrix using the Hough peaks function. The peaks correspond to the intersection points in the parameter plane, so each of these peaks is a detected line. Hough lines function is then used to map the peaks back into the image plane and extract the line segments. Now that we know the workflow to extract the lines in simple images, let's switch to our lane detection example. Let's go back to MATLAB. Let's open the starter script line detection _ start. In this script, we have initial code and comments that will help us build our line detection algorithm. We will first test our algorithm on static images before moving on to a video. We see some test frames in the current folder here in the form of mat files. Let's go back to the script. The starter script already has the first frame loaded. Let's run this to see what this looks like. We see the white lines that we need to detect. Recall that the line detection functions work on black and white images. So we need to threshold this image that will show us only the lines in white and everything else black. This is a thresholding problem, so we can use the color thresholder app to interactively choose the color space and the thresholding limits for our image. We have already seen this before, for example in the blob analysis video. Please refer to that for more information regarding thresholding. Let's go back to the script. Here, we will use the provided utility function createLineMaskHSV generated from the color thresholder app to get the black and white image with the white lines. We will then use IMShow to visualize this black and white image. Let's run this code. We see the white lines corresponding to the lanes here. We also see the white line on the orange cones. This shows that, depending on our application and environment, we might have to perform additional pre-processing before detecting the lines. So in this case, we need a way to remove the orange cones. Let's go back to the script. One way to do this would be to do blob analysis on the image for orange objects, and then block these orange cones with black pixels. We already know how to do color-based blob analysis as we saw in the blob analysis video, so we will use the provided utility function block orange cones for this. We will do this before obtaining the mask lines. So the input to the thresholding changes to the output of the blocked orange cones. Let's also change the plot ordering. Let's run this code. Let's switch back to figure 1. Now we see that the orange cones are blocked. If you look at figure 2, we see that the lines corresponding to the orange cones no longer appear. We see some bordering white sections of the image appear that may need to be removed, but for our sample application, we are okay with this. Next, for line detection to work best, the lines in our image need to be continuous and thin so that detection of duplicate lines can be minimized. We can do this with morphological operations. Let's go back to the script. We will first use a morphological closing operation to close the gaps to make continuous lines. We will use a disk structural element with size 10. Followed by this, we will apply skeleton operation. We can do this using the bwmorph function. Here, we specify the image followed by the operation. This operation is skell, that stands for image skeleton. This is followed by the number of times to perform that operation. By setting this last argument to infinity, we can remove pixels on the boundaries of objects without breaking the objects apart. The pixels remaining make up the image skeleton. This will help us reduce the thickness of lines in the image, thus helping reduce duplicate detections later. Let's run this code. Let's go back to figure 2. Here we see the continuous lines. Let's go back to figure 3. Here we see the skeletonized lines where they appear thin. Note that based on application and environment, other types of pre-processing might have to be done to make the image ready for line detection. Next, let's apply the line detection workflow to retrieve the line segments in this image. Let's go back to the script. Similar to the simpler example we saw earlier, we will begin by computing the Hough transform. Then we will find the peaks in the transform using the Hough peaks function. Finally, we will find the lines corresponding to the peaks using the Hough lines function. Next, to overlay the results on our original image, we will need an array with the points of all the detected lines. For this, we will use the provided utility function getWizPosArray. Let's go back to the command line and open up the utility function getWizPosArray. This function is similar to the array construction that we did in our earlier example, except that since there might be multiple lines detected, we use a for loop. The function returns a formatted version of the line and marker positions for visualization. Let's go back to our script. So let's call getWizPosArray function to get the line and marker positions. We can then use the insert shape function to draw lines on our original frame. We will draw lines in blue with width as 5. We can also use the insert object annotation function to draw markers to denote ends of lines. We will use yellow circles to denote end of line segments. Finally, let's visualize this image using IMShow. Let's run this code. We see the two lines detected. Let's go back to the script. Let's take a look at the workspace. Notice that there is only one peak detected. We see two lines for a single peak because these lines coincide. Also, we see only one peak because we haven't provided a numPeaks value. Let's go back to the script. Let's specify the numPeaks value as 10 in the Hough peaks function so that we can see the 10 largest peaks. Let's run the code again. Let's go back to the script and the workspace. Now we see two peaks, and there are three lines corresponding to these two peaks. Let's take a look at the result here. Here is the third line. Although this line is not what we are looking for, we will leave the numPeaks value at 10 to see if it affects the other frames in the video. Next, notice that these two lines can be connected to make one long line, making the detection less redundant. Let's go back to the script. We can do this by using the fill gap property on the Hough lines function. Let's set it to 100. This is the pixel distance between the two line segments. When the distance between the line segments is less than the value specified, the Hough lines function merges the line segments into a single segment. Let's run the code again. Now we see that the two lines has become a single line. We also see a smaller line that does not correspond to a white line. Another property that might be useful to filter line results is to use the minimum length property. Let's go back to the script. In the Hough lines function, we can set the minimum length property. Let's set it to 100 in this case. This will limit our results to all lines greater than 100 pixels in length. Let's run the code again. We no longer see that small line. All along, we have been working with the same sample frame. Let's use other frames to test our algorithm. Let's go back to the script. Here, instead of frame 51.mat, let's use frame 151.mat. Let's run this code here. We can see the line here. The line here is too thin to be identified, as can be seen from the skeletonized version here. We can work on our pre-processing step to make this better. But for our sample application, we are okay with this. Let's go back to our script. Change this from frame 151.mat to frame 251.mat. Let's run this code again. We can see some lines here. Notice that we can see multiple lines close together in a small neighborhood. We can use the neighborhood size parameter with the Hough peaks function to suppress the number of peaks in a given pixel neighborhood. Any other peak in the pixel neighborhood is set to 0 and ignored. This will help us reduce the number of duplicate peaks. Let's go back to the script. For the Hough peaks function, let's apply an extra parameter nHood size. The default value for this is the smallest odd integer greater than the value of the size of the transformation matrix over 50. In our case, let's give it a bigger size than this to see if we can suppress duplicate peaks. So let's set it to a 2x1 array 55, 11. Let's run this code again. We see that several duplicate lines have disappeared in this area and only 2 lines remain. Now that these results look desirable, let's try it on our video. Let's go back to our script. Let's open the script line detection underscore vid. This has the exact same algorithm that we developed right now, except that it is placed inside a while loop, and instead of static images, we use a video file reader to read our video in frames. Then we use a deployable video player to visualize our results. Let's run this code. We see that the line detection mostly does a good job. There are still some lines detected which we would ideally want to filter out. With further testing and tuning of parameters, performance can be improved. Let's go back to our presentation. We ran through the example of lane detection to follow the Hough Transform workflow by computing the Hough Transform, then finding peaks, then extracting the lines. In the example, when computing the peaks, we saw the effect of number of peaks parameter. This controls how many peaks at most we would like to see. We can see the smaller number of lines detected in case of the default here. We also talked about the neighborhood size parameter. This helps suppress peaks within a region, reducing the number of lines detected in a given area. In this image, we can see that increased neighborhood size results in decreased number of overlapping lines detected. Next, we extracted the line segments using the Hough lines function. This takes in the black and white image as input, theta and rho, which are the output of the Hough function, and then the peaks for which the lines need to be extracted. This is the output of the Hough peaks function. We then talked about a couple of parameters of the Hough lines function. Fill gap can be used to merge 2 line segments within the distance specified to make one long line. We can see example here where 2 lines are merged into one. Minimum length can be used to ignore lines less than a particular length specified. We can see the example here where the smaller line has been ignored. In summary, we talked about what is a standard Hough transform and how you can use it to extract line segments. This concludes this video.